So let me just remind you what a standing wave is. Standing wave is this thing that looks like it's just kind of oscillating in place. It's actually made from the superposition of traveling waves bouncing, or I should not say bouncing, but colliding into each other. And here are some of the ones that I made for you last time. These are just the first three. And what we're going to do now is try to just quantify the equations for what could produce these. So not every single wave can be a standing wave. There's certain rules. And so first, let me try to draw. This is basically the length of the string. Obviously, the string is a little longer because it's bowed, but if we take that they're relatively small amplitude, that's basically the length of the string. How many wavelengths is this?
Half?
Half a wavelength, that's right. So in the length of the string, we fit a half a wavelength. Okay? So that's the half a wavelength. And I think I might have forgotten to mention before, but if this wasn't obvious, the wavelength of the standing wave is exactly the same as the wavelength of the waves that made it, right? All right, so how much in this length of string, in the total length of the string, how much a wavelength is that?
One.
It's one full wavelength. So the individual waves that make the standing wave, as well as the standing wave itself, has a wavelength that's exactly equal to the entire length of the string that we're using. What about this? How much of a wavelength is that? 1.5 wavelengths. Or, as I can write it, as a fraction, 3/2. So there's a pattern here. And the pattern appears to be that L is a integer number of half wavelengths. So in the length of the string, you can fit a whole number of half wavelengths. N can be any integer. N equals 1, 2, 3. So convince yourself that if you plug in n equals 1, 2, and 3, you'll get the three things that we just wrote down. So here we have, of course, just 1 over 2, so that's a half. Here we plug in n equals 2. So the 2 cancels, we just get the wavelength, and then here you get 3 over 2, okay? So n is just kind of a number of integers, but it's a handy way of actually labeling these guys. N equals 1 is this one, n equals 2, n equals 3 is this one, and then the pattern does keep going. At some point I was unable to produce them for you by hand, simply because, as we're going to discover, you have to go to higher and higher frequencies, right? If the wavelength is getting shorter, then the frequency goes up. And at some point I can't move my hand fast enough, but if I could, you would be able to get these, all right? N actually gets a name. It's called a harmonic number. So this is the first, second, and third harmonic. Now, that rings a bell if you're a musician. Does this have to do with something called something you use in music called harmonics? Oh yes. Okay. So we're going to be talking a lot about music today. So how does this all work into music? Other names that you might see in music: n equals 1, the first harmonic, sometimes is called what's called the fundamental. If you've ever heard that, maybe take a music theory class. And then the rest of them are first overtone, second overtone, third overtone. And so the second harmonic is the first overtone. There's an offset in the overtone number and the harmonic number because the first harmonic is called the fundamental, which is a different name. So that's what we find. In the length of the medium that you have, you can fit a whole number of half wavelengths. In fact, n is actually the number of half wavelengths that are in the medium. Now, why does it have to be half wavelengths? Well, it has to be half wavelengths because the boundary conditions are really important. Here, if both ends of the string are fixed, right, they're both held down, then they both have to be nodes. They have to obey the fact that the string can't move on the ends. It can move in the middle, up and down, should it wish to do so, but it can't move on the ends. So we can't just put anything willy-nilly on here. We have to make sure that whatever wavelengths we put on here, it will put a node on both ends. So the nodes are on the ends. Have to have nodes on the ends. Now you can choose to put no nodes in the middle, like in the first harmonic. You can put one node in the middle. There's also a point where the wave doesn't move. It could move there, and it does move there in the first harmonic, but we're looking at all the different options. So as long as you put in 1/2 wavelength, or 2/2 wavelengths, or 3/2 wavelengths, this one will have 2 nodes in the middle. The thing we have to do is put nodes at the ends, because that's where the medium is held down if it can't move. So an example would be like a string inside a piano, right? It's tied down on both ends. So that greatly restricts which waves will have standing waves. Okay? So the whole point of why this is the case is because you must have nodes at the ends if the ends are fixed. Can't have the end be an antinode and be bouncing up and down if it's tied to the wall or something, or tied down, right? All right, so let's keep going. Let's see what we can find out of this. We can invert this equation. So these are the only wavelengths that are going to work. These are the only wavelengths that are allowed on this medium to make standing waves. I might put lambda sub n here just to indicate, because this is going to be a set. Only certain wavelengths work. This wavelength will work, but one that is bigger or smaller by a little bit is not going to work. We have to go all the way down to this wavelength for another one to work. We have to go from this wavelength to this one, which the wavelength is actually going to be half as much. And then I'm going to go ahead and put in, so I know V equals F lambda, right? So there has to be some kind of coordination between the frequency and wavelength, because of course the wave speed is fixed by the medium. So that is non-negotiable. And again, what do I mean by V? You might say it's a standing wave, there's no V. Well, remember, what we mean by V is the traveling waves that are making this standing wave. So both of those have speed. The reason why it looks like it's oscillating in place is because of the result of that superposition. So a standing wave is created out of two waves that are traveling in opposite directions. So I go ahead and put in here V equals F sub n, and I solve my equation. It looks like this. So what this is an equation for harmonic frequencies. N can be any integer. 1, 2, 3. But these are the only frequencies that will work. It's a discrete set. Not just any frequency will do. There's a whole set of them, but there is not any old frequency will do. Okay? So these are the certain frequencies that on this medium will produce the right wavelengths so that the boundary conditions are obeyed, that there are nodes on either end. Any other frequencies will produce some garbled mess, but they will not produce a coordinated standing wave, which is important because when you have the standing waves, you have this coordination where crest and crest line up to make supercrests, and we have these huge oscillations called antinodes. Okay? So what I want to do is I want to explore this equation. This is the master equation for, say, a guitar. So I brought in a guitar today. I'm going to show you how this informs how guitar makes sound. Are there any questions on how I got this before I clear a little space? Okay, so let's do that. So I'm going to look at this. And while I'm at it, let me go ahead and throw in the equation for wave speed on a string, right? So if it's a guitar, it's waves on a string. And we remember that formula we got before? F over mu, right? This thing right here is the wave speed, right? Every single variable in this equation, N, L, F, and U, all have some bearing to how a guitar plays. So let's take a look. There's a guitar. Now, before you ever play a guitar, you might want to tune it, right? So, oh, and I guess I should mention, remember frequency is pitch, right? So if it's a higher frequency, it's a higher note, right? So let's talk about tuning. Now, if I tighten the string, I increase its tension. What is that going to do to the speed of the traveling waves?
Faster.
Increase it. What is that going to do to the frequency of the note being played if everything else is the same?
Increase.
Increase it. So if you tighten the string, the note will be higher. That's what the tuning pegs are for on a guitar. They tighten or loosen the string. Basically, the string winds around it, and when you turn the peg, they will tighten it. So let's try it. So I'm going to play a string. I'm going to tighten the tuning peg. Hear the pitch going up. Lower the tension. Goes back down. Now you might rightly complain your ear is not on the string, but I will tell you that whatever frequency the string vibrates at, it vibrates the air around it in the same frequency, and that's what you're actually hearing, right? You're hearing the sound wave that's being produced by that vibration. In fact, the chamber of the guitar is intended to amplify that. But it is at the same frequency. So the frequency of the guitar string becomes the frequency of the sound wave. That's the thing that's faithfully passed from the string to the air. Okay? So that's something that you normally do before you start playing the guitar, rather than during playing the guitar, but you can adjust the tuning pegs. Many instruments that are stringed, you do this tuning yourself. Something like a piano, which is basically a whole bunch of strings inside, it's very, very complicated, so you might call over a piano tuner and have them do it for you. Okay? But you want the strings to be at about the right tension before you start. Let's take a look at mu. Now, if you increase mu, right, you give the string more inertia, what is it that happens to the wave speed?
Lowers.
Decreases. So what happens to the frequency?
Decreases.
Decreases. Now, if it's hard to tighten a string with the tuning peg while you're playing, it's really hard to be changing the mass properties of your string while you're playing. Okay? That would be challenging, right? You just pluck the string and then throw some mud at it or something like that. Okay? That's not feasible. So how does this inform how a guitar is constructed, or any stringed instrument? Here's how. If you look at any stringed instrument, the strings are not all the same thickness. You will find some strings that are very thin and others that are very thick. And in fact, the ones that are very thick, they make a little scratchy sound. You can sometimes hear it when people are playing acoustic guitar, because it's not just a single string, it has another string wound around it. It's to give it more thickness. So why would you want to do that? Why do you want to hear this when someone's playing guitar? Well, if you didn't have access to having different mu strings, you'd have to do everything with tension, right? You would have to have that the low notes, the strings that are supposed to play the low notes, low frequency notes, they'd have to be very loose, right? And the ones that played high notes would have to be very tight. And it's extremely hard to play an instrument where one string is really tight and the other one's just flopping around. So you don't want to just use tension as your only means of setting a bunch of strings at different pitches to start with. You want to also triangulate with how thick the strings are. So then you can sort of get that the strings aren't too different in tension and they're not too different in thickness, so that then you might kind of sort of be able to play all the strings kind of together, right? So you want to do some triangulation between how tight they are and how thick they are, so that they're kind of sort of all similar zones, right? If you did it all with tension, some strings would be, the high notes would be really tight and the low notes would be really floppy. And if you did it all with thickness, well then you'd have some strings that are gigantically fat and some that are very thin, and you don't, that's hard to play too, right? Does that make sense? Okay. So those are all things that go into first just stringing it, okay? If you've ever played a guitar and you go to replace a string that you broke and you don't have the right one, it's always tempting to throw on another one that you do have, but it's much more liable to snap sometimes because, for instance, if you try to put on a really thick string and crank it up to the high enough tension to make a high note, it's under way more tension than it should be. So that's why you want to put the right string on the right place. Okay, let's look at the other things. Length. Now, the string, I can't make it longer than it already is, but I can make it shorter by taking a part of it and taking it out of the vibration. So I can go from something like this, where I'm using the entire length of the string, to take just this. So I put my finger down here, and I shorten the amount of the string that's actually able to participate in the vibration. And if I lower L, what happens to the frequency? Increases. You will hear a higher note. And this is, by the way, the operating principle of what you do most of the time when you're playing, is you're changing the effective length of the string. So in a guitar, I pluck the whole length like this. It's vibrating between here and here. It's making the n equals 1 harmonic. The ends of the string are forced to not move here and here, and I'm plucking it, and this is the entire length. But now, if I go over here and I press down, there's these nice little metal guides called frets, so that I can, as long as I put my finger anywhere between them, it'll always hold it against the metal, which is always the right place. I pluck it here, it's a higher note, right? Because I'm taking this part of the string out of the vibration entirely, right? It's just vibrating now between my finger and here. So it gets shorter. And the shorter this effective length, the higher the note, right? I'm taking progressively more and more of the string out of the situation. Some instruments, like the guitar, have these frets where you can be sure you have a little bit of error. You can put it anywhere between the frets and the fret will be where it's pinched. Other instruments are harder to play. You have to have your finger be just right because there are no frets. So, for instance, violins and cellos and things like that. The way they get around not having their finger in exactly the right place is something called vibrato, where they just kind of go like this, and they go, right? So it's sort of right, but you can't tell because they're kind of vibrating it, okay? Another thing that sometimes you see, like, you know, if you have one of these blues guitarists, they go like this. They fret something, but then they go, right? They bend it, right? Someone really gets into it, you know? Okay? Why is that making the note higher? Is it because I'm changing the length of the string? What am I doing?
Increasing tension.
I'm increasing the tension, right? I'm just pulling it, right? So that's another way that while you're playing, you can use tension to your advantage. Okay? So that's what you do most of the time when you're playing. But, of course, we were talking about harmonics. So let's talk about harmonics. Okay? So, we should maybe write some of them down. So, V over 2L, 2V over 2L, 3V over 2L, 4V over 2L, like that. That's just some examples. So how do I make one of these? Well, got to be tricky. If you just pluck the string, you will get this. All right? If you want to force this, you're going to have to do something to encourage it to not do the first one. So here's what you do. When you pluck this string, you use another finger gently at the halfway point to force that point to not move. You encourage a node there. So instead of just coming up to it, plucking it from the halfway point, okay, so, which by the way is conveniently marked with these two dots, that's the halfway point of the string. If you pluck it there, you're obviously going to make a big antinode in the middle, and that's what you get. So here's what I'm going to do to get the second harmonic. I'm going to pluck it from over here, but I'm going to hold this finger briefly here at the halfway point to force it to not move, and then I can get the second harmonic. Okay? So you hear that? It's a different note. This versus this. Now, make sure you understand the difference between having the length of the string. I can certainly press my finger down here on the fret, and then I get that same note. This part of the string has been taken out of vibration, right? So this is what I'm playing, and this has nothing to do with anything. That's not what I just did, though. This, if I let my finger go, no, it's gone. But this is the entire string still vibrating, just in a different way, right? So it's still the entire length of the string, but now vibrating like this instead of like this, okay? How can I make the n equals 3 harmonic? Well, I now have two choices. When I pluck the string, I need to encourage either 1/3 of the way or 2/3 of the way. I need to hold my finger down there to encourage that spot to not move. That's how I can encourage the third harmonic. So let me see if I can find that. Either 1/3 of the way, like that. That's 1/3 of the way, and here, that's 2/3. So it's still the entire string vibrating. That's why I can make it happen and walk away. It's still the entire string vibrating, but now in a different way. All I have to do is encourage the right harmonic to be formed when I first pluck the string. All right? Are there any questions on that so far? Okay, so let's talk about how this deals with music. Now, one of the things I want to point out is that the spacing between these two guys is even, or between all of these, right? So the difference between any two adjacent harmonics is V over L. That, by the way, is one of the trickier questions on standing waves on your homework, is that it gives you two harmonics and you have no idea which ones they are. Okay? So they give you two what they call resonant frequencies, which is another name for harmonic frequencies, and they say these are two adjacent ones. Well, you don't know if it's n equals 2 and 3 or 17 and 18. You just know that they're adjacent. Well, it doesn't matter where they are in the series, because as long as you know they're adjacent, the difference between them is always V over 2L. Okay? So if you know the difference, if someone gives you a whole set of harmonic frequencies, as long as you know the distance between, as long as you know how far apart two of them are, you know V over 2L. Okay? Now, that is the equal spacing if you're talking about addition and subtraction, but if you're talking about our ears, we don't hear notes as additive. We tend to hear it more as multiplying. Okay? So what do I have to do to multiply this to get this? 2. Okay? So that's a frequency doubling, right? The frequency doubles. So frequency doubles. Now, what is the significance of a frequency doubling in music? Does anyone know? Any musicians here? No? Okay. it's called an octave. Ever heard of an octave? So an octave is the same note again, but higher, okay? So if you know do, re, mi, fa, sol, la, ti, do, okay, do is the same note as the first do, it's just higher, right? So that's what's called an octave. So if you have a musical notes, if you know musical notes, they go A, B, C, D, E, F, G, okay? So if it's a C, then you double that frequency, it's the next up C, okay? So every frequency doubles is going from a musical note. I guess let me break down the musical scale for those of you that may not know it. Here's musical scale A, B, C, D, E, F, G. And then there are notes in between. There's A sharp, C sharp, D sharp, and F sharp, and G sharp. Is anyone taking any music here? Okay, awesome, okay. So you can, A sharp is halfway between A and B. It's also called what? B flat, right? B and C and E and F are tricky because they don't have anything between them, okay? So that's 12 notes total, right? That's the Western chromatic scale. It's 12 steps. There are other music traditions that, most notably Indian music, that break up a octave or frequency doubling into way more steps. But this is the Western music. So what you do in music is you take every frequency doubling and you break it up into 12 roughly equal steps. Okay? Does that sort of make sense? So every time the frequency doubles, you are back at the same note. And to get there, if you do it in 12 equal increments, that was what we call the Western musical scale. Now, if you go to the next harmonic, is that a doubling? It's not. In fact, if you have to get rid of the 2 and put in a 3, so divide by 2, multiply by 3, that's 1.5, right? So that's times 1.5. That's not an octave. In fact, here it gets even smaller. You have to divide out the 3 and put in the 4, so that's times 4/3. So these harmonics get progressively spaced, closer and closer. That is not the steps of the musical scale. And in fact, let me play it for you, and you'll see that. Here's the fundamental, n equals 1. If I go to the next one, it should sound like the same note, just higher, right? That's an octave. Does it sound the same? I've doubled the frequency. N equals 1, n equals 2. The next one is not going to sound like that. It's going to sound like this. I'll keep going. Oops, let me do them in order. N equals 1, 2, 3, 4, 5. I guess that might be confusing to you, the order that I'm doing them with my finger. I'll slide my finger progressively this way, right? Because I'm going to try to catch the first note every time. I'm kind of cheating, and sometimes I'm jumping to another note because they're close together. So n equals 1, 2, note is halfway. Then this one, the 1/3 of the way. Then this one. That one, and then so you see the first note is moving progressively closer and closer, right? Goes this way, and then it gets closer and closer and closer. Okay? So if you are restricted only to the harmonics, you don't get every note in the scale, right? You don't get all of these. You only get some of them, right? So that's why you need ability to manipulate more than something than just harmonics, right? You want to be able to fully manipulate the length of the string as well so that you can get whatever note you want. The frets, of course, here are put in, if you look here, so there's no frets, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So you're taking the halfway point of the string and you're putting in 12 steps. And you can see that the spacing actually is not even uniform. If you want to make that Western musical scale and you want to make the frequencies into 12 equal bins, then you have to make sure that the fret spacing is just perfect, right? So that's how a guitar, cello, violin, even a piano is a stringed instrument. That's how they all work, okay? Now let's move into other instruments. Well, any musical instrument is based on standing waves, okay? The only difference is what is the standing wave in. If you get to flutes, clarinets, saxophones, didgeridoos, whatever instrument like that, it's a standing wave in air, okay? If you want to even get into things like drums, right, those are standing waves on a membrane. So, for instance, a snare drum, it makes a two-dimensional standing wave on a circular membrane, and the note, of course, is around the rim because the drum skin is attached there. Now, that's a whole complicated thing to do two-dimensional standing waves. You can get the idea, but the math is much more difficult. But let me focus again on musical instruments that are basically in one direction. And if they're in one direction, that's basically like a string, except for it's a column of air that you're putting the standing waves in. So let me do that. Now, I posted the applet for you before, so I didn't bring it back, but you can play around with these. You can have that both ends are closed like this. Now, I'm not going to try to draw the molecules because that would be a mess, so let me just draw the pressure variation, okay? Or let me draw the displacement variation. It's going to look like this. If you have a closed tube, remember that the air molecules can't move there, right? This is the boundary conditions. They have nowhere to go, right? There's a closed end. So that's the first thing that obeys the boundary conditions, right? And then the next one might look like this. This is really deja vu, isn't it? These look the same, right? It's the same formula. The only difference is that instead of using F over mu, instead it's a sound wave in air, so you can't really do much about the wave speed. It's 343, right? So that's the only modification you need to make. Now, if someone were to point out, well, they just look similar because it's the displacement amplitude, right? This in the length of our tube, we're able to fit a half wavelength, and that's why it looks the same. Why not draw the pressure variation? So we talked about the fact that when you have nodes and antinodes, if you have a displacement node, you have a pressure amplitude, and vice versa. So I could certainly superimpose here what the pressure is doing. So if the displacement amplitude is nothing, you can't move, the air molecules can't move because they're trapped against the end. I was talking about before, like if you're against a barrier at a concert, right? If you can't move, you're going to get crushed. So the displacement nodes are the pressure antinodes. So that would look like this. Oops. That's wrong. Let me try it again. That would look like this. So notice that the pressure nodes at the ends have switched to, the displacement nodes have switched to pressure antinodes. And what used to be a displacement antinode in the middle is now a pressure node, right? So if you're in the middle of the crowd and you can move a lot, right, then you can just go with the flow and you're not crushed, right? So if you can move, if you're a displacement antinode, you're a pressure node. Now let's just double check. How much of a wavelength is that in terms of pressure? if I switch the nodes to antinodes and the antinodes to nodes, how much a wavelength is that? Still a half, right? It's still a half a wavelength. Doesn't change anything if you flip perspectives, right? Doesn't matter. Formula is still the same. In fact, if both of your ends were open of your tube, you can also get a standing wave like that. There, the only difference would be is that since the air is free to move, then it would be the displacement that has the antinodes on the end, because you're free to move, and that means that it's going to be pressure nodes. So it just reverses it. So this is going to be a pressure node. The pressure doesn't vary on the ends. In fact, what is the pressure on the ends if you have an open tube? Atmospheric pressure, right? So the pressure doesn't vary from atmospheric on the ends. So here's my suggestion to you. This equation is very universal. The only thing that is required is to have like ends, okay? That the two ends of the string or the tube, whether they're both closed or both open, the only thing that matters is that it's like ends, okay? The only case that we need to, oh, and I guess let me show you one of these guys. Here's a tube. Both ends are open, okay? Can make a standing wave in this. There's one. There's the next one. There's the other one. Right? It's the same progression as this, right? Start from about the same note. Right, same notes. Okay. You can make standing waves in air. That's what you're doing with a, any wind instrument. So one case we need to address is what if both ends are different, right? So this equation is the like ends equation, but it is possible that we have that the two ends are different. So let's do that real quick. Using the same procedure. Let's make it so that it's like this. So I guess first let me draw S max, the displacement. So here, of course, you can move as much as you want because the end is open, but here you can't. So that's what this standing wave looks like. This is a antinode for displacement, and here they can't move at all, right, because it's a closed end. This is the length of the tube. How much of a wavelength is that? From a crest to the next equilibrium. It's a quarter. So in the length of the string, or length of the tube, I've got a quarter wavelength. Right? Let's do the next one. The next one that you could fit in that looks like, that fits the one end being an antinode and the other one being a node, right? Because they have to we have opposite ends that doing different things. So the next one I could do would look like this. Antinode here, node on the end. That's the boundary conditions, that always has to be true. And I do have one node in the middle as well. How much a wavelength is that? It's tricky. It's 3/4 of wavelength. I guess I'll draw one more, just for good measure. The ends have to be an antinode and a node, because they're opposite. but now I'm going to slip 2 nodes into the middle instead of 1, so that's going to look like this. So you can see that's the common thread, right? Is that you have to have that the end conditions are obeyed. In this case, they're different ends, antinode and node, and then I progressively slip more and more nodes into the middle, right? So first no nodes in the middle, then 1 node, then 2 nodes in the middle. This one is a wavelength and a quarter, or 5/4. So what's the pattern here? The pattern is a little bit odd. The pattern is that in the length of the medium, you can fit quarter wavelengths, but only odd quarter wavelengths. So you can confirm that this equation, plugging in 1, 3, 5, 7 odd numbers, will get you these. So this is a little bit strange, is that we skip numbering. We call this the n equals 1 harmonic. We call this the n equals 3. So in a tube like this, with different ends, you only have odd harmonics. N is the number of quarter wavelengths now. Remember, it was the number of half wavelengths before. Now it's the number of quarter wavelengths, and odd only. Okay? So if anyone ever shows you a picture of one of these guys and gives you nothing else, the first thing you should do to try to figure out what it is, look at the ends. Are the ends different or are they the same? Okay? If the ends are the same, count half wavelengths, and however many half wavelengths you get, that's your harmonic. So you can say that's the whatever harmonic. That's the 6th harmonic because it has 6 half wavelengths in it. But if you look at that wave and you see that the ends are different, then you have this situation, then you should be counting quarter wavelengths. And if you see 7 quarter wavelengths, that's the 7th harmonic. And if you count 6 quarter wavelengths, you're using the wrong thing because you shouldn't be able to find that. This is odd harmonics only. The only difference in this is the 4, so the equation, when we ... derive it, looks like this. And this is your equation for the frequencies that will produce standing waves for unlike ends, whenever the ends are different. So on your homework, that's really the only decision you have to make. Are you using the previous equation we had for like ends? In the denominator, you had a 2 instead of a 4. And of course, every n number will do, not just the odd ones. So you just have to look at the situation and decide if the ends are like or unlike. All right? So let me give you some brief examples here, and then we will break for the day, and looks like we'll finish standing waves. Let's take musical instruments. Let's take wind instruments, okay? Or what we call them wind or brass instruments. They're both basically standing waves in air. The only difference is whether you have what's called a reed or not, or if you just blow directly into it. One of the things that you're limited here by, of course, is V is fixed, right? V is 343 meters per second. Now, L, same deal. If your L decreases, your frequency will go up. Okay? So that's what the keys are mostly for, right? Is to change the effective length of air that you're vibrating, right? You will, by the way, also find that instruments that play high notes are very short for that reason, right? A piccolo or like those things are very short. The length is small, so the frequency is high. All the instruments that play low notes are very long. So if you know what a didgeridoo is, right? Very long. Tuba, it's so long that they take the tube and they kind of go like this with it because it's got to be really long. Okay? What if you had an instrument that had no keys? You can't vary V because it's standing wave in air. You can't vary L. What's the only thing you have left? N. So you cannot play anything except the notes associated with the harmonics. You might say, who would make such an instrument? Well, there is such an instrument. It's called a bugle. It's a trumpet with no keys, presumably so that they don't gunk up on the battlefield. So in a bugle, you may have heard, there's this song like Charge, Let's Go Get 'Em. Right? That's better. You heard that? Let's Go Get 'Em. Right? That's just the harmonics. I think it's the 2, 3, 4, and 5. There's the, I think it's called taps. Have you heard this song? It's all just harmonics. Bugle, you have like basically 4 or 5 notes total. That's all you have. They're all made out of the same notes. Okay? The other thing I wanted to show you just to close out, give me 1 second. Here I have a slide whistle. In a slide whistle, you get to see the direct effect of length. Trombone works the same way. You can continuously vary the length. If I make the length shorter, the frequency will go up. So, check this out. Right? Okay. Now, let's compare 2 instruments. Flute, clarinet. Now it turns out that for a flute, it can be thought of as having open ends. I'm not going to get into why that is, but it's just how it's constructed. A clarinet has unlike ends. So let me make a comparison. A flute and a clarinet are about the same size, right? They're not hugely different. So L is about the same. Let me take a look at n equals 1 for both of them. Of course, V is the same for both of them. So the only difference is the factor of 2, right? The factor of 2 and the factor of 4. What it tells us is that for the clarinet, the flute is about 2 times the frequency as anything else. So this explains why a flute sounds much higher than a clarinet. It's simply because of the construction. If you don't believe me, let me try it here. So I play this. Okay, that's with the unlike ends. Okay, one end is open, one end is closed. Then I'll plug this up. Oh, sorry, I did it the wrong way. So this is the clarinet. This is the flute. It's about an octave, right? Double. So this is with both ends being different. I'm actually causing vibration with my blowing. So this end is closed, this end is open. You can see there's a little hole in there. So that's like the clarinet. And then when I make both ends open, doubles. Okay, so that's it for the standing waves unit. We'll do the Doppler effect on Friday.